Hello, everybody, and welcome to the fifth subtopic here in this in topic 8, supporting cognitive functions. And this is the last one we'll do with the cognitive function of memory. So 8.3 were the basic models of memory. 8.4 talks about the process of encoding and retrieval, shifting ideas back and forth between working memory and long-term memory. This is a little more about how we can design for both of those types of memory, working memory, long-term memory, and proper encoding and retrieval. Just a few things to add on to those two introductory topics. Okay, so we remember one of the things about working memory is its capacity, which follows that magical number 7 plus or minus 2 concept. So I can keep about 7 plus or minus 2. Let's be on the safe side and just do 7 minus 2, not go higher than that. So 5 to 7 is about what we can expect. People have capacity slots for doing whatever they're doing at the current moment. So if you can assume that a human will get one chance to get a message, and then they have to act on that message, you have to consider that they can only carry 5 to 7 chunks of information with them in acting on that. So if I go over here and I read the manual about what I need to do, and if the manual says, all right, turn on the power, then check the message in window A, then check it in B, and it gives me this complex sentence as the first instruction, okay? Well, I got to store all of that in my head and then go over here and act on it. And I've only got my working memory to carry that information with me. Now, if I forget something, maybe I can turn around and go and reread the manual or whatever, but that's inefficient. That's a wasted sampling, a wasted message delivery, so to speak, right? So we want to design for that capacity. And, we say 7 plus or minus 2, let's be on the safe side and say 5. But there's actually evidence that shows, well, it's not like we're only like, if we're doing something here where I've got a new computer program, it's not that that's the only thing that I'm thinking about at all at the time, right? There are other aspects, of reality, of being alive, of being physically present in a space that are also going to consume some of my working memory, not necessarily in like a chunk sense, but when you're trying to do multiple things at once, this ideal 7 plus or minus 2 capacity kind of gets strained. So as a good rule of thumb, and empirically this seems to work out, if you have high workload or running memory tasks, running memory meaning like, remember this and do it, and now you got to do another thing, or you got to remember the next thing or whatever, then use no more of these than 4 of these chunkable units of language, which we'll call a proposition. Okay, so I've underlined them here in this message, but let's see. Turn on the power, turn on power, check message window A, check message window B. When light is green, comply with message window A. So, I'm taking out all the filler words there, but the essence of what carries, what carries a concept would be, what we call these propositions. So you're going to think about that when you're designing, especially verbal, linguistic sorts of aspects, but it's of message displays, for example. But it stands for more than just words; it's chunks, right? So 5 to 7 if people are in a relaxed context, 5 to 7 items they might keep in their working memory between receiving an instruction and carrying it out. But if people are doing something like driving a car, which is going to consume some working memory capacity, right? It should. Then, driving a car and trying to process everything that's here and combine it all together, and doing the mental math to determine, okay, it's 6:17 a.m. right now, am I within one of these windows? Mental math consumes working memory slots as well, right? So consider that these are all tasks where you can't really easily stop and really deeply process this, and then, oh, if I mess up, I can turn around and come back to it. This is probably something you are processing in passing. There's a limited window of time in which you can devote information processing resources to it. Here's another one. Assuming these two are designed to be read while driving, they are poor designs. They're including potentially, I would say arguably, more than 4 propositions that have to be processed at once in order to get the essence of the message. This one here I really like because, it's silly. Left, right, left, right, left, right, left. Actually, that's not that hard to remember. Left, right, left, right, left, right, left, because I've just chunked a series of directions into this pattern. Now I just have to remember, oh, you just keep alternating left and right. I'm remembering, one thing or fewer than all of those individual directions. But, consider that if you need to evacuate a building, you might be under certain levels of stress. Maybe the building's on fire. Generally, we're not looking for emergency exit instructions unless we have to exit in an emergency. And under those, under those mental conditions, our working memory is even more limited. Okay, so remember that. So again, the magic number here, 4, is about what, good design standard to go for. Okay, now working memory is better and better when we can take advantage of the way we encode information. We talked in the last lecture about some of those memory tricks, like the guy who could, have the deck of cards and see them and interpret them as this is Tiger Woods hanging out with Abraham Lincoln and Lady Gaga. And that's a more visual representation, taking advantage of the visual spatial sketchpad, right? So make sure you know that very well. Visual spatial sketchpad and the phonological loop being 2 of the storage systems from Baddeley's model of working memory. So we're going to take advantage of those sub memory functions, storage systems, and how encoding tends to work well in, like learning learning contexts, excuse me. All right, so the optimal chunk size, if you have, let's say, a random string of things like numbers or letters, is about 3 to 4. So, phone numbers, typically we will report them in groups of 3 and 4. Similarly, like our social security numbers or federal IDs, student IDs, they tend to be grouped in numbers. And that's easier to remember than 7 items. It's 2 chunks, right? And of course, I also note 555. By the way, this is a nonsense. I don't think there are really phones that use this. It's sort of like a Hollywood representation of you're making a phone number, but it's still 555 is still something that, to some of us, to me at least, there's a certain inherent meaning, like phone number. That's a chunk that goes with phone number. So when we talk, I've got that coming up here, inherent meaning behind these things. Okay, you're trying to get somebody to remember something like a phone number. Pictures are going to be the most informative. Actually, this is just in general showing the efficiency of information processing is highest for pictures, meaning for the least amount of invested effort, I can gain the most information with a picture. Seconded by letters and then by numbers. So I can gain more information. They're also, because of the way that it can relate to other letters, let's say, letters are more memorable than numbers, which is why you typically would see 1-800-GET-THIN instead of 1-800 and then whatever the digits are that are represented there, that would just be, much more difficult to remember. So not only am I associating this concept of, hey, call this number with images, that are associated with what that could happen if I call that number, I am taking advantage of essentially chunking principles to take otherwise a random string of digits, or apparently random, and it's much easier to remember this way. 1-800-GET-THIN is much easier to remember than 1-800-783-5947 or whatever. All right. Remember that when we use our phonological loop, it is very similar to speaking out loud in terms of things like confusability. So remember, we had that string of like similar sounding letters when you enunciate them, E, D, G, B, V. That's harder to remember a string of those than it would be different sounding, characters or letters or numbers. So this extends then beyond just, individual characters, words, that sound similar if you speak them out loud. They're also going to be harder to maintain in your phonological loop. Meaningful sequences like 555 or ABC, much more easily chunked, much more easily grouped together there. And if you have letters and numbers, or pictures, letters and numbers, separate them, because then in a way we're able to chunk each of these just by the nature of, is it a letter, shape, or number. So if you can do so, it is going to be supportive of the way that our working memory works. All right, so that's designed to support. Oh, I think we got one more. Yep. Remember again my example of when you go to the grocery store and you're trying to remember all the ingredients for the sandwich. And one of the ways to do that is to visualize yourself making the sandwich. And this would take advantage of the very strong image-based visual spatial sketchpad memory, that could be quite robust, and it takes less effort to remember more complex things if they can be encoded in a spatial pattern. So, if my passcode is this, and I'm trying to remember in my head 237640722, and if I try to use my phonological loop to remember those numbers and I'm repeating them in my head, you'll notice it's more than, wait, how many is this? Oh, it's 8. So it's more than 7. So it was challenging me to keep those in my head. But you might recognize this. Some of you are saying, oh, I don't do it that way. I just go with the shape. And I would say, yeah, that's absolutely the right thing to do, because a shape is going to be more reliably rememberable. You can store it in muscle memory almost. And then you're no longer having to, internally speak, verbalize the what goes with these, with your passcode there. So just thinking of the shape will have less of a burden on your memory, or at least your working memory, than, this full thing. As often as it makes sense to, let's externalize, things that people shouldn't have to rely on their fallible memory to cue them on. Reminders for things, use external aids that capture attention, that tell you what you're supposed to be reminded of. It frees yourself up, from having to rely on an unreliable attention capturing sort of system there. Yeah, I mean, taking notes, like I said, this is an external memory aid now. You can take notes in your phone. You can record yourself speaking. This is all, ways to remember something without having to, take precious, brain memory space, putting signage for the steps that are necessary, as opposed to having to train everybody and expect them to remember, this in an emergency context. Now, when we bring things from long-term memory back to working memory, there are easier ways to do that, and there are harder ways. And one of the main distinctions that we make in this is the concept of recalling information versus recognizing information. And it doesn't always work. You don't always get to choose, but I think you'll see the difference here in terms of the effort. So if I say, well, what is the capacity of working memory right now? You know this. It's been stored in your mind. And some of you may say, I think it's like something plus or minus something. I can't quite remember, maybe take a guess, 5. Right? So right or wrong, it takes a little more effort to bring this answer, the answer to this question, or the related information that you've stored in your long-term memory related to capacity of working memory. You're going to bring that into your working memory to answer the question. Or maybe you have this sort of a question. So which of the following is the capacity of working memory, or which is the closest fit? 3 chunks, 7 plus. Okay, so now why is this different? Because I'm still giving the same answer. Well, what I'm allowed to do in this case, in recognition, you can say, well, which is easier? I hope it's fairly obvious. Multiple choice exams are easier than free response exams, right? And I could be asking the same question, but if I give you some possible answers and one of these is correct, and that, it's much easier for you to, ooh, this is, I don't have to remember entirely that it's 7. I don't have to remember this verbatim. I can just remember, I know there's a plus or minus in there somewhere. So suddenly I can easily, reduce the possible answers here down to fewer and fewer. And then I say, oh yeah, I think, it's got to be that one. I now I remember, so reactivating something with a level of detail that's already present in the world is easier than bringing this entire piece of information unprompted out of the, or without basically comparative options in front of you. All right, so how can we take this now to design? Well, keep in mind, there's a lot of things, that people may need to know but not remember instantly. Like, hey, what does this one font look like? Or where is that one? What's that one font called that looks like this that I need it to look like? And I can either rely on my recall memory, which is difficult. The way I've just described that shows already how difficult it would be to encode that in an absolute sense. So hey, which one do I want if I've got these really awesome block letters with, or whatever. So then what I'm doing here, and this is, a pretty standard feature now for most word processors, is I'm choosing the font and I am seeing right there, I'm recognizing what that font looks like. So I don't have to remember exactly what the name is, how do you spell it in order to type it in that box. I can just look and recognize which one I was looking for, right? So it's much easier to be able to recognize than it is to recall. So we want to support recognition as often as we can in our human systems. Okay, designing to support long-term memory is kind of difficult to say, hey, like just long-term memory. When you're designing to support long-term memory, you're really designing to support retrieving things from long-term memory when it's appropriate to do so. Okay, so we want to support recognition, rather than recall if we can help it. So helping people, have multiple choice tests as they're going through their day makes, each individual, memory task a little bit easier. And the key here is, you're triggering a memory. You're basically bringing something into consciousness that's linked to something, more information, like why is it important that I wash my hands? It's just a matter of me being triggered at that moment when I could wash my hands that, oh yeah, I will do it. So you got to put these cues, if you're trying to support recognition, put them in appropriate places that will attract attention. So they'll trigger this need to act, or they'll trigger this memory cue. And then using other system design features like, making sure that the signage and the attention capturing aspects are near what you'd need to do next, right? I'm putting this sign right on the bathroom mirror because assumedly, or ideally, the sink is right in front of me here, right? So like, oh, yeah, did I wash? I forgot. Thanks for triggering my memory. I'm about to go do surgery. So in any case, yeah. So the proximity compatibility principle, we remember this from displays. Remember, it's one of my favorites. This is a good example of these at play here because I am including a display or effectively, a set of instructions very proximal to some sort of control or other aspect of the system I'm about to interact with. All right, and that's it for memory. Thanks, everyone.